Good morning, everyone. I am Hai Vong, and I work in DISA Emerging Technology Directorate. We would like to welcome you to today's technical exchange meeting. Karambit.AI will present its software behavior assurance for safety and cybersecurity in today's session. I need to go over some administrative items before we get started. First, please mute your DoD 365 Microsoft Teams sessions. Second, this session being recorded to allow future groups to present the capability by members of DISA and DoD community. Third, this is a public forum. No proprietary sensitive information should be shared in this session. Fourth, we encourage questions during the session. So please use the raise hand function in the Teams menu to alert presenter when you have a question. You can also enter your questions in the chat area at any time during the presentation, and the questions will be addressed in the order received. I must provide the following disclaimer. This technical exchange meeting does not infer any intention by DISA or Department of Defense to enter into an acquisition, contract purchase, or endorsement of the presented capability. This session is purely for informational purposes only. We do not control how session participants will proceed with the conveyed content. Access into the technical exchange video, slide decks, and other TAM artifacts will be made available through the TAM website. A link to download today's TAM session slide deck will also be made available in the chat area. With that said, let's commence with the presentation. So over to Karambit.AI for presenting.
All right. Thank you so much for the introduction. So I'm Andrew Mandela, one of the co-founders of Karambit.AI, and I get to show you a bit more about how we do software behavior assurance, both for safety and for cybersecurity. So it's always good to have a bottom line up front. So as I think a lot of people know, attackers have been increasingly compromising software supply chains, including the Department of Defense. This has hurt warfighter readiness, and it makes it risky to onboard new and innovative software. What we do at Karambit is we make the software supply chain safe by verifying software behaviors. And we find behaviors associated with safety, cybersecurity, and effectiveness. Like, is this thing doing what we expect it to do? And we can do this without the need for source code or executing the software itself. So by doing this, we increase safety, decrease time to field software, and eliminate remediation costs by stopping problems before they impact production and mission success. For those of you in the government, we are currently awardable on the Platform One marketplace, so it's an avenue for you to work together with us if you would like to. You can also click this link that's in the slides that Joseph already shared, and you can actually see a quick 5-minute video of our capabilities as well. As far as TRL goes, we are TRL 9 we are actually working in Microsoft's software supply chain scanning platform right now, finding hidden behaviors, and we validate that in production. And for them, we are scanning over 4 billion files every month. We have a TRL 7 capability and some other capabilities a little bit lower in the TRL spectrum, but we have done Linux behavior analysis for Docker containers. We've also done some analysis of drone autopilots and medical device firmware for both safety and efficacy for subsystem analysis. So we'll show you a little bit more about that. As far as past performance goes, we finished a JFAC, the Joint Federated Assurance Center OTA for that Air Force Platform One Docker container behavior scanning, and we're currently on contract with ARPA-H, which is essentially the DARPA for healthcare for cybersecurity and safety of medical device firmware. Now I'll get into the rest of it. So why do we exist as a company? So we started actually right after the Solarwinds attack happened. So my co-founder and I, our background is actually offensive cybersecurity. So how do you find bugs in software? How do you automatically exploit them? Sometimes how do you automatically patch them? And we saw the Solarwinds attack happen, where attackers inserted hidden malicious behaviors in the Solarwinds software. And according to Microsoft, it was the largest cyber attack ever. It compromised over 18,000 public and private organizations. And we realized that the ways people were trying to solve them, things like software bill of materials, which is good, but just gives you an ingredients list, or vulnerability analysis, again, important, but it's not going to solve the problem of hidden malicious behaviors. And then these attacks kept happening. So the high-profile ones like the 3CX attack, or last year with the XZ-utils backdoor, where that was an open source library that had 5 Russian actors ostensibly pretend to be one person submitting really good code for 2 years, becoming maintainers of an open source project, and then adding a backdoor that compromised the security and integrity of SSH, one of the underpinnings of the entire internet. But it's not just commercial software. China also has compromised like an F-35 contractor, and that forced an expensive software rewrite. So this is a problem that's going across all kinds of different industries. And in order to solve this problem, you have to be able to answer the most important question of cyber risk mitigation, or honestly, software risk mitigation in general. If I use this software, will it cause problems? And we do that by validating software behavior and confirming this software is working as the developer actually intended. And we do this by way of automated reverse engineering to provide what we like to call a software bill of behaviors. So this is the list of behaviors in a piece of software. And then we provide on top of that analysis of what are the risks of these and what are the risks in this particular piece of software. So as software changes, we can say, hey, this update, what are the newly added behaviors? Are those strange? Are those weird for this particular piece of software? And are these associated with potentially malicious activities? We aggregate all of that, and that enables us to discover malicious or safety critical behaviors hidden in your software before it goes into deployment, before it goes into production. And this way we can keep our customers from being compromised at all. And that use of historic functionality is unique. And it's not just us saying that. In fact, the reason we have our contract, we are working with Microsoft in their supply chain scanning platform, is because they know too that we are unique. So you can see right here, it's that our use of a content's historic functionality and that changes sets us apart from traditional static analysis. So here's an example of what that actually looks like in practice. So this is an example of us comparing the behaviors from one version of the XZ-utils software, the one that got that backdoor in it, between the benign version, which was 5.4.5, which was in Ubuntu, and also the malicious XZ 5.6.0 was also in the Ubuntu Debian repositories. So we were able to pull these while it was still compromised. And you can see here, and there's a really big point I'm going to make here, is no behaviors are inherently malicious from a cybersecurity perspective. I think my favorite example of this is full disk encryption. So this is something that your IT security team has probably already configured on your device. Your data is going to be encrypted at rest because this is a well-known cybersecurity requirement. However, that exact same behavior, encrypting your hard drive, encrypting your data, is something that ransomware is going to do. So it's intent that makes the most sense. And we provide context of the historic functionality to help understand what the intent of this software is. So you can see here on the left, there's actually not too many cybersecurity relevant behaviors. So they're doing data manipulation, right? Encryption, decryption, encoding. And they're also interacting with the host operating system. But we were able to extract from the malicious version a lot more behaviors that are at first just a little suspicious, and then bump that over to malicious. So we can see, okay, allocating memory dynamically. Okay, that's not necessarily going to be a malicious activity. A lot of software is going to do that. But this particular function that was having that wasn't doing it before. And it's like, okay, they're doing dynamic function resolution. Okay, it's fine. Oh, it's employing evasion techniques. So this, from a cybersecurity perspective, is really important because this means when the attackers put in this malicious code, they were trying to evade different kinds of defenses. And we're able to actually use those evasions as an indicator that something is wrong in the software. You keep going. Okay, it's enumerating and manipulating processes. Again, this isn't inherently malicious, but it's definitely highly privileged. This is the sort of thing like, if you're doing it in a non-malicious way, you're probably an antivirus. As you can tell by the previous version, it was never doing this before. It's not expected. It was doing table manipulation. Oh, it's performing code injection. It's modifying control flow. All of these behaviors we're able to automatically extract and characterize. And this way we can catch these kinds of attacks before they go into production. So what is a lot of the industry today doing? So as I briefly mentioned before, there's a big push in the cybersecurity world for software bills of materials, which are important. It's very important to have your ingredients list. But this is the equivalent of looking at the side of a cereal box and saying, okay, I'm glad there's all of these random things in here. Okay, there's wheat, there's some random chemical, like who knows, but I'll trust that it's okay because that list isn't going to give you the indicator that something is bad. The thing you really care about is the little thing at the bottom where it's like, okay, what are the allergens? What are the things that may cause me harm? And this is something that vulnerability detection generally tries to do. But that's more about, hey, could an attacker use this vulnerability to get in? But it's not going to look at malicious behaviors. If you wanted to look at malicious behaviors or safety behaviors or any of these things, you would have to do either manual reverse engineering or, like we do, automated reverse engineering. But if you're doing it manually, it's going to be expensive, it's going to be labor intensive. You're not going to be able to do it at the scale that we're capable of. But through that automation, we can have a large impact. So we can eliminate remediation costs. So we can help you find those hidden and safety critical behaviors before deployment. And that means you're going to have less time spent remediating problems because you find them before they become problems. We also help you deploy things faster because we can quickly identify, okay, this version right here is good. We give you deep insight and help you understand, okay, yeah, use this one. But I think the most important one for us is we extend the concept of zero trust into software. So we let you verify the software you already trust. You don't necessarily just have to believe and trust the entity that created it. You can actually verify the software you're bringing into your ecosystem. And this allows you to intimately understand what third-party software is capable of. You can stop here. Does anyone have any questions so far? If you have questions, feel free to raise your hand in the middle. And I always prefer that. All right, then. Let's go on. So we're going to get into some of the specific use cases. So first, top of mind for me is scalable cyber behavior analysis. So we can look at first and third-party software and figure out, okay, what is this thing going to do and what are the risks? And this is primarily how we work with the Microsoft Trust and Security Service team. So this is where they have, this is their supply chain scanning platform. We scan about 4 billion files every month. It's probably a little bit more now, but it's been a little bit since we've checked. So this way we can discover hidden malicious behaviors in software before they go to their customers. I just saw the question. I will answer that in a second. Yeah, so keeping customers from being compromised. And for Microsoft, we actually allow them to enforce disallowed behavior policies. So they have certain sets of behaviors that they say, hey, let's never let this into our ecosystem. We allow them to enforce that. And enforcing policies is actually really important because if you don't have a technical control to keep a policy enforced, you're essentially just telling an attacker, okay, do these things because we don't want it to happen. Hi, you said, can the platform provide a detailed report of what was scanned or stopped? What do you mean by that? As in, like,
So I mean, like when the tool is scanning the system, right? So is there any file that's been skipped, or it will scan all the files? It is a detailed report that generate to tell the administrator which file that is scanned or is not. Over.
Yes. So yeah, that's exactly what we do. So we do our analysis. The goal of our analysis isn't to do it on a machine; it's to do it before deployment. So that way, yes, as we're scanning your system, and I guess I can just quickly show an idea here. I was going to get into the demo later, but I can just say it. So here we have this list of behaviors. We've files analyzed, and we can kind of go in and say, okay, what do we have? And this one in particular was completed, and we can give you an idea of like, okay, well, there were 20 files in Alpine Linux, the Docker container. And then we can kind of show you, hey, was anything suspicious? No, we scanned 20 out of 20. So we scanned all the files, all the binary files in here. And then we give you a deeper understanding here of like what was in there, what files, and what the behaviors are. Does that answer your question?
Yes, sir. Thank you.
All right, thank you. Robert.
Yeah, I'm trying to figure out architecturally how you set up. I'm assuming that if I've got a application I just bought and I'm going to put on a server, I'm going to install your software on my server, and it's going to watch the actions that is occurring as the software is running. Is that correct?
No. So that's actually one of the things I was just mentioning. We will scan your software before deployment. So we are static behavior analysis, and essentially what that means is we find behaviors and analyze them without running the software. So you would, depending on the implementation for the production. So for Microsoft, we're doing that on-prem. So we don't see their files. We scan them on their side before it goes to production. And then we get some anonymized telemetry back. But for like the case you were talking about, depending on the sensitivity of the data, we could either do on-prem, or you could upload that via our API before deployment. We would give you a scan report and say, hey, this is good to go because it's doing all the behaviors that are expected for the software. Or we can say, hey, it looks like there's a few things that are hidden in here. Here's our characterization of those.
So again, go a little deeper into that. So as an example, I've got an EXE that's part of my new software. When you scan it, how are you identifying the behaviors? Are you reverse engineering it and seeing the code?
Yes, we're reverse engineering. We're disassembling it, and then we're generally built on top of Ghidra, so that's the NSA's reverse engineering framework. So we take that disassembly, and then we have a proprietary engine on top of that to turn disassembly into behaviors. And then from there, we have our AI portion to determine, is this suspicious or malicious for the context.
You mentioned some of the things you were doing analysis on earlier. Do you also look for attempts to make external connections through the software?
Yes, let me. libcrypto. So yeah, so here's communication. So for libcrypto, it received data of the socket, send data on the socket, so we can find those functions within the behavior. This is libcrypto, so it's actually expected to send and receive data because it's doing the cryptography for like SSL or TLS. But yes, we find that capability.
Well, in this case, we'd be looking for create outgoing socket, right? Not just send receive.
Yeah. Correct. Like that's at a different layer, but yes, like so you can do like a listening socket versus those sorts of things as well. Generally, like we're looking at the data being sent, but we can do either. You say something, Stephen? It looked like you're.
Oh, am I flashing? I guess I am curious, is this a laundry list? So you sort of, I'm going to use the word signature. It's not really a sig, but are you saying, all right, here's 100 behaviors that we know how to detect, or is it more generalized than that? Does the AI do a black box stinger on it?
A little bit of both. So we have like custom, I'll call them signatures because it's close enough. Or types of behaviors we're interested in, because those are the kinds that attackers have to use. So again, if you're going to send data out, you do send the data out. So there is a rule set there. For more of the safety and like effectiveness analysis, that's more generalized. But it's very easy for us to generate new rules. So we're doing that at a regular basis, especially as attackers are changing how they do their obfuscations and changes to combat detections of like antivirus and EDRs. We're constantly changing our algorithms to be able to find those new and exciting types of behaviors.
This is Eric. I'm Andrew's co-founder. I'm just following up really quick. So the there is a layer of signatures, like Andrew said, and then on top of that, especially for the kind of safety analysis that Andrew was talking about, we take those kind of signatures, which we find are generally very reliable, and then we apply algorithms on top of it to say, hey, we've noticed a whole bunch of these network behaviors in this area of code. Now we can kind of analyze all the surrounding functions and say, this is probably the network component entirely. That looks very different for different kinds of software. So one of the packages we looked at not too long ago was a patient monitor, and so we're able to find things like this is blood oxygen measurement functionality, and that's not something that any signature base we build would have. But we're able to take fundamental kind of behaviors and signatures and then use that to create a higher level language of here are the higher level behaviors.
Okay, yeah, thanks. That architecture makes a lot of sense.
All right. Any other questions before I keep going? All right. So again, here we're talking about this scalable analysis. And one of the things I mentioned just now was attackers and obfuscations. Like these are some of the ways that attackers hide themselves. So we've actually seen from this data set, this massive data set we've been getting from Microsoft is we're able to see how attackers are changing and how some of our more general analysis. So less about specific, hey, here's Packer Dictator. It's one of the Packers that we've been able to discover in the data set. But we have more general things like Packer Generic Island, Packer Generic Overlay, things that are more generally ways that attackers are going to hide themselves. And we use that as indicators of, okay, something new is happening here. If we can find it, let's get more specific. Similar method, similar idea, more general behaviors. We can also detect AI and ML in the software. And this is important for Microsoft because they particularly want to understand, okay, where is AI and ML occurring in our ecosystem? This is very important for compliance. It's not necessarily a blocking behavior, but it's something that I think both large organizations within industry as well as federal government, we would like to know about. Okay, who is actually using AI? How are they using it? And this is our work towards that. And then, of course, I already mentioned this. I kind of talked through it, but it's not just close. It's not just closed source that may have hidden behaviors in it. Even the XZ-utils, which was ostensibly open source, their malicious behaviors didn't show themselves until it was compiled and in particular way. And that's why we look at the compiled binaries rather than just the source code, because there can always be differences between what goes in one side of the development pipeline and what comes out the other end, just like in the Solarwinds attack. But more than just obvious malicious behaviors, sometimes libraries are just risky, and you won't necessarily know about what things are capable of unless you do deeper analysis. So in this particular case, we did analysis of Galera 4. Well, we did analysis of a lot of the open source libraries that were on Ubuntu. And we realized this one, okay, it has the ability to execute a shell command received from a socket. It's a replication framework doing transactional stuff. So it's not necessarily malicious, but it's something that if you're going to do a risk assessment, you need to understand, okay, what is this software capable of? And do I want to allow that in my ecosystem? We already had a bunch of questions on this part, but I'm going to go to Docker container next. Any questions on that? Or I guess any more questions on that? Okay. So for this, I already showed you a little bit of one of the analysis we did for Alpine. But Docker is used, obviously, all over the place. It's underpinning nearly every cloud service you use. So one of the things we've done in the past is we actually processed all of the Air Force Iron Bank Docker containers. So this was last year during that OTA I was talking about, and we were able to process 1,500 Docker containers. And we extracted all of the ELF binaries. That was about 1.7 million. Those deduplicated down to 174,000. And we were able to extract, analyze, and find a series of things like anti-analysis. That's like, those are the ways, again, that attackers are using evasion, command and control, and other behaviors. But context is really important here because there's no inherently malicious behaviors. So secure shell, SSH, it has command and control behaviors because that's what it does. It connects out of the network, so you can securely connect and run commands on another machine. So it's not necessarily malicious, but again, important to understand. But one of the key findings we realized from this is extracting all of those files from a lot of different things in their ecosystem. We could also detect if one of these files claims to be the same version of a particular like library or executable, but it's different behaviors. And this isn't necessarily malicious. It obviously could be, but sometimes there's different compiler options. So they'll have more or different kinds of behaviors. But this capability provides the ability to have a gold version of a library. Say you analyze a bunch of different versions of a particular file and you say, hey, this is the one I want to use in all of my system. Let's get rid of all the other ones. And let's make sure that all of the behaviors are validated. Any questions on that? It's pretty short. Right? So, oh, yeah, Robert.
So just curious, so you are identifying suspicious activity within the code that it could be doing. And then somebody's got to go through and sort of whittle it down and go, that's normal, that's normal, that's normal, that's not normal. Where do you see that that action taking place at the user level, or do you go back to company X and say, what the heck is this going on?
There's a few different ways of doing it. One, the reason why we want to bring in that context of previous versions of a piece of software is kind of lower that burden, right, of false positives of, back to this, like SSH, it's going to do command and control. Bringing in that context can help say, okay, that's not something you're interested in. But whether or not we go back to the vendor is a different question. So for some of our current work, we're actually working with vendors to analyze their software before it goes into deployment, and that way we can communicate directly with their developers and say, hey, here's the results. Can you explain why this is doing this? Like, this looks very highly privileged. It may be expected for the software, but let's work through that. But it also depends. So another example for Microsoft, we focus on things that are very highly targeted. So because we're scanning billions and billions of files, you can't have a lot of false positives. So we're focused very deeply on, okay, things that we know are accurate 100%. And that helps lower those false positives and make it more streamlined. But it really depends on the end user. If they want to go back, they might just say, hey, this thing is risky. I don't want to use it at all. I'm not going to bother going to my vendor. Or they might want to go to their vendor. Very similarly, if you're a developer and you're pulling in, a Docker container, right? And you say, hey, this one's doing a bunch of behaviors I don't want to do. Well, you can suggest, okay, switch to a different Docker container that doesn't have those behaviors. So we give information and we help them understand. Does that answer your question?
It does, and just kind of a follow-on to it, when working with the different customers, or in your history of having the company around, have you identified the true, like, this is definitely a bad function, it was not meant to be in there, kind of stories in your use cases?
We definitely have. Those are not ones that we can generally share on an open line.
Gotcha. And I'm thinking open source, whatever, I just downloaded XYZ open source thing and we found 15 bad things in it, as an example.
Okay. I mean, like, so XE is one very easy to talk about. Like, yeah, we have the capability to find things like that. We have some other risky behaviors. We found, I'll talk in a bit about a backdoor. Actually, that was the next thing I was going to talk about, is a backdoor in a patient monitor from China, the CMS 8000. So I can talk about that as well. But I will get to that in a second. I think there was another question. Oh, Jasmine, she posted that in there. Well, this might answer your question, Robert. So can you hold that until I go through this, and then we can ask more? Is that all right?
Holding tight.
Thanks, Robert. Okay, Jasmine, you may have mentioned this. What range of tools are built into the solution? So generally, the tool set is our proprietary engine built on top of Ghidra. So it's not necessarily a whole range of tools that are external to us. A lot of it's proprietary binary analysis. But Eric might be able to give more details if you would like, Jasmine. So maybe I should. I guess if you're typing. I can wait until the next set of questions if you want more details. So for this next set, we talk about product behavior assurance. So there's a lot of work again focusing on, okay, is there a vulnerability in this? What are the ingredients list? But we've been doing work basically doing deep dive analysis to analyze products that are going to go into high assurance environments. So think Department of Defense, civilian government, medical devices, aerospace, etc. And this way, we can provide behavior validation and details at a variety of different levels. So sometimes executive, sometimes for product security, sometimes just the developer teams. And there's obviously different levels of technical acumen at those different levels. But the idea here is, and I think this might actually talk a little bit more to the question we were talking about before, Robert, is we can basically verify, okay, are these behaviors that are expected? And if there's something unexpected in their software, help them be able to fix those and confirm that they're actually fixed. And this is either long form, PDF, JSON for integrations, an API. But if you look over on the right, we actually did analysis of a patient monitor that came out of China. It was approved by the FDA, I think 14 years ago. It's called CMS 8000. And it is a well-known now, publicly reported backdoor. And we were able to, it was found manually, and we were able to put it into our analysis engine and both detect and characterize that in natural human language. So this is one of the big things that we've been adding in, is not just, okay, we found the behavior, but how do we characterize that? And how do we help make risk decisions? So you can see here, we have a bill of behaviors. It's creating sockets, it's receiving data, it's sending data. As Stephen was pointing out, it's sending and receiving data, not necessarily, we're not here focusing on making the socket itself. But you can look on the right, and this is our more general reverse engineering behavior analysis, where we can actually summarize the function operations. And you can see here, it is actually mounting a network file system from this hard-coded IP address. And this IP address is actually an IP address for a Chinese university. And it just mounts it, sees if, checks for mount monitor, and then it just copies all of those files right to pin, and then runs it. And we're able to characterize this correctly as very, very high risk, because these operations are lacking the visible checks and balance mechanism to authenticate or validate user permissions. So it's a behavior that could look like a standard update mechanism, because again, no inherently malicious behaviors. However, it was lacking a lot of those visible checks and balances that would indicate that it was more benign than malicious. So this in particular is a piece of a backdoor that we can talk about pretty openly. We can go into some arbitrary detail. Do you have any questions on this, Robert? I know you were asking.
No, that's exactly what I was looking for.
Okay, perfect. And what's interesting, I mean, what's really interesting for us is this was we just took the firmware and put it in. So it kind of shows that it's not just a matter of, okay, Windows software, it's not just Linux software, it's also embedded software that we have the capabilities of analyzing, finding behaviors, and characterizing them. So from there, actually, are there any other questions? Now I'm going into our more safety analysis. So
yeah, This is Steve Bruckner, DISA.
Yeah.
Do you or can you also take as an input the release notes of the software as an accompaniment to, I see you smiling.
Oh no, because this is something we haven't done yet. But what's really interesting, well, actually, there's a couple. So I talked a little bit earlier how we have TRL 9, like we're in production with Microsoft, like TRL 7, a little bit lower on that research threshold is we actually have been doing some work generating release notes from the binaries and from their differences, and then that allows us to compare. But we haven't done a lot of the work necessary to we haven't done enough experiments to compare those or to take in those release notes and say, hey, this is working as intended from the release notes. But it's something that's shortly on our roadmap. But
actually, one thing I want to point out, Andrew, is for this patient monitor, there was documentation around what was submitted to the FDA for, I'm sorry, I forget the name of the form, but there's a form that details out like what this monitor is supposed to do. And we fed that in as part of our inputs, and that's how we're able to additionally get like, okay, here are different types of functionality in the binary, and it helps us triage and search for things. I imagine readmes and changelogs would be very similar. We just don't often do it because a lot of the times we're working off of binaries and kind of going with the vendor and speaking with them directly.
Okay, cool. Thanks for the answer. There's obviously all kinds of ways you can take this. It's glad to hear that one. It also ties into, in the solution space of supply chain risk analysis tools, where does this sit? Automated versus standard, dynamic versus static, yada. I'm not asking where it sits. All right, so this is a comment, not a question. But yeah, where it sits in that space versus how DoD could use it directly versus how software vendors would be using it is in mind. So over.
So that's a comment, not a question, or
yes. Sorry, I'll turn it into a question at the end if appropriate. Thank you.
Okay. All right, that sounds good. Yeah. So as Eric was mentioning, and I was going to get to that, and he rightly mentioned it. There's a thing called a 510K summary, and those are public. So those give things like indications of use, like, hey, when would you use this particular device? Descriptions. So we've been able to import those to help us find some of the stuff I'm about to talk about. So this is more safety effectiveness. What is this thing doing in a more general way that we've been working on? So the first thing is sometimes, so the FDA, again, did not approve this particular patient monitor for wireless monitoring. They did approve it for wired monitoring. So you can say, hey, there's network communication over a wired protocol right up here. However, we were able to take the firmware and extract all the functionality that existed, but shouldn't have from an approval perspective for doing network communication over wireless protocol. A lot of times, it seems like on the regulatory side, they focus more on, okay, what did the vendors tell us, and we'll trust them, but it's harder for them to verify. They're changing that. They're getting better about that. But one of the things is they didn't tell them they had wireless capability, so it wasn't able to be approved. But we were able to detect that. But on top of this, we also were able to characterize the software functionality in a more general way. So we can find things like medical device communication, signal processing, signal management, healthcare monitoring, the things that are really core to a patient monitor, the things that are affecting health and safety. And then other things like, okay, dynamic display and interface management, thread creation, a lot of these general behaviors. But here we can dig in a little bit further. So for the medical device functionality, we're actually able to go in and extract, the physiological waveform display and update. So there's a lot of functions that do that. And this is actually like the line for your pulse that you're seeing. That's the physiological waveform. We found the 11 functions in the patient monitor that do that. ECG, right? Pulse. We can find the device initialization and the data processing, the thing that's actually calculating your pulse to send to the other piece. CO2, SpO2. We found that functionality. We can see that signal processing. We can see how and then from there, we can see how those different subsystems are interacting, what they make function calls. We can notice that from sensor input or physiological data collection, it does go up to encryption and decryption before sending things out. That's very important to understand from a cyber risk assessment, threat intel, things like that. Any questions on this? Anyone want to raise a hand, or I can read Stephen's question? Okay, so how confident that some of these risky behavior code snippets are reachable by all potential execution paths? I'm thinking that many might be disabled based on configuration or input. Okay. We wouldn't necessarily care if they're reachable by all potential execution paths. Just from the perspective, like, we would be most interested if it is reachable at all, because that just might be a rare behavior. This is actually one of the reasons why we do static analysis, because that way we can still find rare but potentially safety critical behaviors. But yes, some input paths just might not be might be disabled based on configuration or inputs. Yeah, no worries. I understand. Yeah, any path. So that is part of it. As you can see here, we're doing some graph analysis to be able to determine things like that. But actually, on the cybersecurity side, it's actually really interesting, because sometimes you may look at it and you say, oh, this might not be reachable, but it's a callback function. So it doesn't look reachable until it hits a particular thing you're looking for. So from a cybersecurity perspective, a lot of times, like if a risky behavior exists, it might actually be better to remove that risky behavior if you don't ever want it to happen. And that's a different level of analysis and modification. But doing things like this where we can check to see, okay, how are these functions interacting, is very important for exactly what you're talking about. Does that answer your question?
Yeah, I started typing before your slide here, but thank you.
No worries. There's a lot to this, and maybe we can talk offline to go into more. And here's a little bit more on this. Not just here's the graph, here's the way things are processed. We can also use the way things are processed to help give an explainable, human readable understanding of what this thing does. So from that analysis, we can say, oh, here's the measuring, here's the processing, here's the preparation of the data, here's the data transfer. This is obviously a lot prettier of a graph because we did this one manually, though it was from our automated analysis. But you can take the generated analysis and tell, how is this data flowing? Is it coming from the network? Is it coming from healthcare devices? Is it reads medical device data? And how is it sending it out? And we have more detail in this, obviously. You can only put so much on a slide. So any questions on this on the medical device side? Right. Then just to make sure we're not saying, oh, this only works on medical devices. We also did this analysis on a drone autopilot. It's a PX4 autopilot. It's a publicly available automated UAV control software. And this is going to be a lot more complex of a system than a medical device. So you'll see there's a lot more going on here. And you can see the slides that Joseph posted again. So you can dig into this if you want. But just like before, we're able to dig in ourselves and say, okay, this particular cluster, what kinds of capabilities are in it? So we were able to find the UAV navigation and control functionality. So things like, hey, here's the vector math and calibration. These are these transformations. Okay, here's the navigation control, and here's the flight navigation, obstacle detection, geofence management. So we're able to automatically extract that capability. And this is really important, especially if you're going to do a software update. Hey, this works now. If that software update is going to affect something like obstacle detection or geofence management, that's going to be problematic from a flight worthiness perspective. So we can help better understand that. And again, check the clustering, see how that architecture is interacting. And you can see like, oh, there's the sensor and control systems and how that interacts with the aircraft, the navigation, the control systems there. So just another example, yeah, we can do this not just for medical device firmware, but also things like drone firmware, things that are very high assurance. Any questions on that piece? All right. So this will be a bit of our final use case. So we've been talking a lot about cybersecurity risk and maybe individual instances of software, but we use these as building blocks to understand the risk analysis and behavior and function changes in software updates. So as we were talking about, okay, we have the drone, we have the navigation system, we have the medical device, we know where the medical device functionality is. If you're updating this piece of software, we can then give risk assessments of that software update itself. So we can say, hey, what behaviors changed? Are they going to affect safety? Are they going to affect the clinical behaviors? Are they going to affect that essential behavior to this device? Did it add risky or malware-like behaviors? Did any of those change? And then we can help triage what that looks like. So in one of our exemplar updates, okay, it updated 10% of the functionality. Then we can characterize, okay, which one of these have made major changes, which ones are minor. Okay, this one had, most of these are minor. We can give human readable explanations as to why we think those are minor, as shown below. And this way, we can help kind of streamline that process of, okay, this update did or did not affect that core, say, business logic of the device. It's just something doing ancillary to maybe patch a vulnerability. And this way we can help get those patches out and show the risk quickly. Any questions here? And honestly, I've been really appreciating the questions, so thank you, everybody. All right, then I think I kind of briefly touched on this, but who am I? My co-founder Eric is also on the call. We've been doing cybersecurity, deep cybersecurity research for over a decade together at a few different companies. We've done work in cyber attribution, exploit development, malware analysis, vulnerability research. Eric, he was already talking, but he is awesome. His background is scalable program analysis, offensive cyber, and he also helped develop one of the autonomous bug hunting systems for the world's first all-machine cyber hacking contest, DARPA Cyber Grand Challenge. So he's great at what he does, and I'm just so glad that we were able to found a company together. All right, so this is the end of my slides. I showed a demo already a little bit. I can go a little bit more into that. If you're interested, you can sign up for a free account. Check out the thing that I was just showing earlier with the demonstration. Any questions? Or would you like me to dive into a different portion of the demonstration? Thanks, Rendell, for posting the link. Stephen, you're unmuted. I don't know if you wanted to say anything.
Yeah, I'll let you do some demoing, and then maybe engage with you after the recording stops.
All right. So I was already talking a little bit about this. If you do sign up for an account, you can actually just click here and upload. I'll re-upload Alpine because it's the thing that's easiest for me to upload, since I did it recently. You can see all the different things processing. As you can tell, I was testing my demo beforehand. We already dug into Alpine earlier. Don't need to renew that. But we can look at some of our differential reports. So here we have diff for the liblzma. This is the XZ-utils attack. And we can actually show you right here what are the differences between the two pieces of software, the two different versions. So we can see that the sizes, the malicious one is a little bit bigger, has some more functionality, has some more instructions, but it's really the behaviors mapped back to the MITRE attack framework that really help us understand, okay, what does this software do? How has it changed, and what are the suspicious things? So, okay, dynamic function resolution, map to attack, execution, shared modules, evasion techniques isn't necessarily mapped very clearly to one particular MITRE attack framework, but manipulating processes, so process discovery, code injection. So as I mentioned before, there's a lot of these behaviors that just have been added by the threat actors to be able to evade antivirus and to do their backdoor injection. But then the baseline piece of software didn't really do a lot of these, what we like to call risky or highly privileged behaviors. And we're able to bring in that context to say, hey, this is very clearly something got added in here. But it's not necessarily always going to be something malicious, right? So here, for instance, we have libcrypto 1.1.0 and 1.1. This is actually ARM. We're able to process more than just x86, x64. We can do ARM. Pretty much anything that Ghidra can support, we can support to one level or another. And the nice thing about Ghidra is it's extensible. So there's an architecture that it's support for. It's relatively straightforward to add new architectures. But here, this is the risk score A. Like this is good to go. There's not any new malicious behaviors. It's just doing things in different instances than I did previously. So help streamline the process. Give a quick run through and say, okay, this is okay. But one other piece of software I really like bringing up is this particular version of PuTTY. So a few years ago, North Korea used PuTTY release 7.7 and added a backdoor to it. So if you had something like a software bill of materials, all you're going to see is, oh, this is PuTTY, it's release 7.7. These are the same thing. You can't tell without behavior analysis which of these had the backdoor and which one didn't. So because we're able to compare these two, we can say, okay, the one with the backdoor in it was doing more file system manipulation. It added an encrypt and decrypt, a couple of extra functions for encryption and decryption when it really should have been using the library that it already was using. Instead, the attackers added in some functionality to use the x86 extensions instead. But what's really interesting here is it was also doing additional data collection, reading clipboard data, scheduling tasks via the command line. It was doing some persistence mechanisms. So once you ran this, it scheduled a task, so it was going to keep doing that. But the reason I really like bringing up PuTTY is it's a really good point on how there are no inherently malicious behaviors. So PuTTY, it's a Windows secure shell client. So both the benign and the malicious version have the ability to create a reverse shell. So this is a capability that normally attackers will use to evade network defenses. So if you're inside a network, if you're an attacker, you're already inside the network, you can't connect from the outside into your implant. You go from your implant back out, and that's a reverse shell, and then you allow commands to be run on the device inside the network. But this is naturally what PuTTY does. This is what a secure shell client is going to do. So therefore, it's not malicious for that reason. It's malicious for the other reasons, and we're able to bring in that context and help give that understanding. So any other questions? Kind of walk through a few of the things that are in our website now. As I mentioned before, we're continually implementing more and more algorithms and getting them into the website so that we can show them. Anything else, everybody? I'll go back to
yes.
this.
So what is your you got to sign up for? Yeah, here you go. What does this give you?
Yeah. So free account, just as I said, you can go. It'll log in. It'll give a very similar dashboard to this, except when you log in, it won't have any files analyzed. You can scan, you can upload things, you can see how our technology works. You can look through and experiment. It focuses mostly on the cybersecurity aspects, not the safety and effectiveness in those clusterings. That hasn't been integrated into our front end yet, but it is a fully formed capability.
I think search for hashes also work, Andrew.
It should. It should, Patrick. Eric, does that right now?
I think so, though, Patrick, since the last time you probably looked at it, we've changed it to search like within a scan. So if you uploaded like a Docker image, I think the searching is for finding a hash within a package. I will double check.
Makes sense. Thank you. Just trying to make sure the context for everybody that might want to search a specific hash might not even be able to find it. Thank you.
All right. Thanks, Patrick. For context, Patrick is one of the people we work with at Microsoft. So appreciate you being on. Any other questions?
This is Hai from this to the audience would like to ask if you have any question, please feel free to ask at this point. We're open for the question and answer. Over. So it doesn't appear there are any other question from the audience. For Karambit.AI, would like to double check if you have any kind of final thought for the audience before I close out the time session. Over.
No, I really appreciate everyone's time. Thank you for the great questions. And if you want to chat more, here's my contact information. Thank you.
All right, thank you so much, sir. So with that said, if anyone interested in pursuing this capability, company contact information is listed on the screen right now and also in the chat area as well. If you don't feel comfortable to contact the company directly, please feel free to contact my organization, this Emerging Technology Directorate. We can help you to get in touch with the company on your behalf. So I would like to thank Karambit.AI for presenting their solution and addressing all the questions from the audience. Also thank everyone for your time participating in this time session as well. And thank you very much, everyone. I wish you all have a wonderful day. Bye now.
Bye. Thank you all.
Thank you.